Download this code from codegive.com, link in the description below. Advancing Diffusion Models for Text Generation, a comprehensive tutorial. Diffusion models have revolutionized image generation, and their application to text generation is rapidly gaining traction. This tutorial provides a deep dive into diffusion models for text, covering the fundamental concepts, advancements, implementation details, and code examples to help you build your own text-generating diffusion models. Introduction to diffusion models. Diffusion models are generative models that learn to reverse a gradual noise process to generate samples from a desired distribution. They consist of two main phases. Forward diffusion, noising process data, in our case, text, is progressively corrupted with noise, example Gaussian noise, over several steps. This process transforms the initial data distribution into a simple, tractable distribution, typically Gaussian. Reverse diffusion, denoising process. A neural network is trained to predict the noise added at each step of the forward diffusion process. By iteratively subtracting the predicted noise from the noisy data, we can gradually reconstruct the original data, effectively sampling from the target distribution. Why use diffusion models for text? High quality diffusion models can generate high quality and diverse text samples. Flexibility. They offer flexibility in conditioning, allowing you to guide the generation process with specific prompts or attributes. Controllability. Diffusion models can be steered to generate text with certain characteristics or styles. Theoretical foundations. Grounded in statistical physics, offering robust theoretical understanding. 2. Key concepts and terminology. Forward process. The Markov chain that gradually adds noise to the data. Defined by a variance schedule beta_1, beta_2, beta_t, where t is the total number of steps. Reverse process. The Markov chain that gradually removes noise from the data, starting from pure noise. Learned by a neural network. Diffusion steps, t the number of steps in the forward and reverse processes. A larger t usually leads to better results but increases computational cost. Variance schedule, beta_t controls the amount of noise added at each step in the forward process. Common schedules include linear, cosine, and quadratic. Noise predictor, epsilon_theta. A neural network, typically a transformer, trained to predict the noise added to the data at a specific time step t. This is the core of the denoising process. Conditional diffusion. Conditioning the reverse process on external information, such as a prompt, class label, or other attributes. 3. Challenges in applying diffusion to text. Applying diffusion models to text presents some challenges. Discrete data. Text is discrete, while diffusion models are naturally suited for continuous data. Variable length. Text sequences have variable lengths, requiring padding or other handling. Computational cost. Training diffusion models can be computationally expensive. 4. Techniques for addressing the challenges. Several techniques have been developed to adapt diffusion models for text generation. Denoising diffusion probabilistic models, DDPMs, with discrete latent spaces. This involves using a discrete variational autoencoder, V, to map text to a discrete latent space, then applying a diffusion model in this latent space. This tackles the discrete data issue. The V learns a codebook of discrete tokens, and text is encoded into sequences of these tokens. The diffusion process then operates on these token sequences. Denoising diffusion implicit models, DDIMs allow for faster sampling by reducing the number of diffusion steps. They achieve this by relaxing the Markovian assumption of DDPMs, allowing for larger jumps in the denoising process. Mask diffusion models. Instead of adding noise, these models mask out tokens in the input sequence. The reverse process then involves predicting the masked tokens. This avoids the need for a discrete latent space. Examples include mask GIT. Vector quantization. Quantize the embedding space of a pre-trained language model. The diffusion model then operates on these discrete quantized embeddings. Implementation details. Building a simple text diffusion model, DDPM with discrete latent space. Let's walk through a simplified example using the DDPM approach with a discrete latent space. This example will focus on the core concepts and will require adaptation for larger datasets and more complex models. We will use PyTorch for this implementation. 1. Setup and dependencies ***. 2. Define a simple V, for generating the discrete latent space. 3. Define the forward diffusion process ***. 4. Define the noise predictor, denoising network. A simple transformer-based network to predict the noise. 5. Define the reverse diffusion, sampling, process ***. 6. Define a dummy dataset and data loader ***. 7. Training loop ***. Explanation of the code ***. 1 V***. A simple V is used to map text to a continuous latent space. The encoder maps text to a mean and log variance, which are then used to sample a latent vector. The decoder maps the latent vector back to the text space. This example assumes that the text is already tokenized with integer token IDs. 2 Forward diffusion ***. The linear_beta_schedule function defines a linear variance schedule. The forward _diffusion_sample function takes the latent representation of the text and a time step and adds noise to it. 3 Noise predictor ***. A transformer-based network predicts the noise added to the input at a given time step. 4 Reverse diffusion, sampling. The sample function starts with random noise and iteratively denoises it using the trained noise predictor. It uses the DDPM sampling equations to step backward through the diffusion process. It decodes the final latent space using the V to generate tokens. 5 Training loop ***. The training loop trains both the V and the noise predictor. The V is trained to reconstruct the input text, and the noise predictor is trained to predict the noise added to the input at a given time step. 6. Advanced techniques and considerations. Conditional generation prompt conditioning incorporate prompts or conditions into the noise predictor network. You can concatenate prompt embeddings with the input embeddings or use cross-attention mechanisms. Classifier free guidance train the noise predictor with and without conditioning signals, example prompt embeddings. During sampling, extrapolate the prediction based on the conditioned and unconditioned predictions to guide the generation process. Improved architectures larger transformers use deeper and wider transformers for the noise predictor to capture more complex dependencies in the text. Attention mechanisms experiment with different attention mechanisms, such as multi-head attention, local attention, and global attention. Training strategies gradient clipping clip gradients during training to prevent exploding gradients. Warm-up schedules use warm-up schedules for the learning rate to stabilize training. Distributed training train the model on multiple GPUs or machines using distributed training techniques. Discrete latent spaces with vector quantization. Use techniques like vector quantization variational autoencoder, VQV, to learn a discrete codebook for representing text. The diffusion model then operates on sequences of these codebook indices. Evaluation metrics. Use appropriate evaluation metrics for text generation, such as perplexity, blue score, rouge score, and human evaluation. 7. Code example, classifier-free guidance, simplified. To demonstrate conditional generation, let's add a simplified classifier-free guidance example. This requires modifying the noise predictor and the sampling function. Explanation of classifier-free guidance implementation. 1. Noise predictor CFG *. An additional condition embedding layer is added to embed the conditional input, example prompt. The forward method now accepts a condition argument. If a condition is provided, it's embedded and added to the input sequence embeddings. 2. Sample _CFG *. This function takes an additional guidance _scale parameter. During the sampling loop, the noise predictor is called twice, once without the condition, predicted _noise uncond, and once with the condition, predicted _noise cond. The final prediction is a combination of the conditional and unconditional predictions, scaled by the guidance _scale. Predicted _noise equals predicted _noise uncond plus guidance _scale *, predicted _noise cond, predicted _noise uncond. A higher guidance _scale means the generation process will be more strongly influenced by the condition, the prompt. 3. Training loop and the forward diffusion sample function are modified to send a condition when training. 8. Conclusion. This tutorial provides a comprehensive overview of diffusion models for text generation. We covered the fundamental concepts, challenges, techniques, and implementation details. By implementing the provided code examples and exploring the advanced techniques, you can build your own text-generating diffusion models and contribute to this exciting and rapidly evolving field. Remember that this is a simplified introduction. Building state-of-the-art text diffusion models requires significant computational resources and careful experimentation. Good luck.